welcome back. Let's continue with diode circuits. So today let us look at a circuit called clampers. So first let us take up the definition. So clampers, in simple terms, it is nothing but a DC restorer circuit. Now what do you mean by DC restorer? A DC restorer circuit basically adds DC level in the output waveform. So you will give an input waveform which is a bidirectional signal. It could be a sinusoidal signal or triangular signal. So a clamper, what it does is it will either add positive DC level in the output or negative DC level in the output. Okay, so a clamper can be of two types. So positive clamper and a negative clamper. So a positive clamper or a positive DC restorer circuit which basically adds positive DC level in the output. On the other hand, a negative clamper would add a negative DC in the output. So that's the definition. Now, what is it comprising of? So a clamper consists of the following elements. So it is consisting of a PN junction diode, a capacitor, and a resistor. So it's a simple circuit comprising of three elements: a diode, capacitor, and a resistor. Now the main task in a clamper circuit is that once the capacitor is charged, we should not allow the capacitor to discharge. That means to say, the capacitor must serve the purpose of a battery. So once it is charged, it should retain that particular charge. So capacitor should work as a battery. So that's one of the prime requirement of a clamper circuit. Now, to work as a clamper circuit, the time constant of the circuit, say tau. Tau is defined as the time constant of the circuit. The time constant of the circuit, which is basically product of R into C, should be very large. Should be very large. So as a rule of thumb, what we do in design is that the time period we will consider in the picture. So this RC, the product RC, should be very much greater than, it could be, as high as 10 times the time cycle. 10 times the time cycle. Example, time period of the input waveform is 1 millisecond. Then the product RC should be, very much greater than 10 times the time period. And what's the time period? We have assumed time period as 1 millisecond. That means to say RC product should be greater than millisecond. And R and C are unknown, so you can assume either R value or the capacitor value. So you can assume, say, C is equal to a very high capacitance value. You can assume, let's say, 100 microfarad. So, once you assume this capacitor, you will be able to find the value of R. So, R should be something like very much greater than 10 milli divided by 100 micro. So, that will give you some ohmic value of the resistance. So, this is how we, decide the value of R and C. So, value of R and C are selected in such a way that the time constant of the circuit is maintained very, very high. So, once we ensure this condition, what happens is that even if the capacitor gets discharging half cycle of the input waveform, due to the high time constant, the capacitor will not get discharged. Okay, and which is analogous to DC battery condition. So in a clamper circuit, which is perhaps a very important summary, in a clamper circuit, due to the high time constant. Okay, so time constant is nothing but product RC. Once the capacitor is charged, it is going to behave like a battery. Battery as in, it will not discharge. Okay, whatever may be the circumstance. Okay, so fine. So as we have seen that there can be two types of clampers, right? Positive clamper and a negative clamper. So first let us try to understand the working of a positive clamper. What you have to understand is that in case of positive clamper, you can carry out the analysis using ideal diode, as well as you can carry out the analysis using a practical diode. And you can also construct a biased positive clamper. So in case of biased positive clamper, what we do is we insert an external battery and we will try to limit the charging level of the capacitor value. Okay. So positive clamper, let us consider. So first let us look at the circuit. So it is comprising of a capacitor. So this is the position of the capacitor. This is where you will keep your capacitor. Resistor will be measuring the output voltage. So this is your input and this is the capacitor. Okay. So as I was mentioning that clamper is basically comprising of three elements: capacitor, diode and a resistor. So next comes the working. So working of a capacitor is split into two parts. The first part is finding out the charging voltage. So you can call it as charging cycle. So we want to know, to what voltage level the capacitor is being charged to. The second one is the output cycle. Once the capacitor is charged, you may proceed to find the output voltage. Okay. So first let us consider the charging cycle. So in charging cycle, our aim is to find the charging voltage of the capacitor, that is Vc. Okay. So initially it is assumed that the capacitor is uncharged. That means to say there is no initial condition exists. There is no stray voltage which is present across the plates of the capacitor. Okay, so Vc is 0 and we will identify the charging cycle. Okay, so you have to identify the charging cycle first. Okay, so charging cycle as in you have to identify the half cycle of the input that will forward biases the diode D. Okay, so if you look at this particular circuit, you can clearly observe that if you consider the very first negative half cycle of Vi, you would see that the positive terminal of Vi is connected to anode terminal of the diode. So when the positive terminal of Vi is connected to anode terminal, we would say the diode is forward biased. So in case of positive clamper, capacitor gets charged in the very first half cycle of the input. So in the working, first let us consider the charging cycle. Okay, so using charging cycle, you will be able to determine Vc. So Vc is the value of the charging voltage of the capacitor. Okay, once Vc is found, then you can find the output voltage. So output voltage can be found using the further analysis. Okay. So in case of positive clamper, what you have to do is you have to identify the half cycle of the input which will forward bias the diode D. So in case of positive clamper, if you begin with a negative half cycle of Vi, you would see that in the very first negative half cycle, the diode is forward biased. Okay, so that's what I have written the summary over here. Capacitor gets charged in the very first negative half cycle of Vi. So once the capacitor gets charged, you will be able to find the voltage. Let's see how exactly we determine the voltage. So in order to determine the voltage, let us draw the equivalent circuit for the charging cycle. So negative half cycle we have considered, right? And here comes the capacitor, and diode is going to get forward biased, right? So under forward biasing mode, diode acts like a short switch or closed switch. This is your resistor R. And this is the output voltage V0. Okay. So let us mark Vc as the capacitor voltage, and from the fundamentals of charging the capacitor. So this terminal, let us say terminal 1 of the capacitor, is connected to negative terminal of the source, hence terminal 1 attains negative polarity and the other side attains positive polarity. So this is the polarity which is assigned to voltage based on the capacitor charging phenomenon. Okay, and one can also comment on the output voltage. If you clearly observe in the very first charging half cycle, the diode is going to get forward biased, and you are basically observing the output across the load, which is nothing but the short circuit terminals. As you can see, the terminals of the load is short circuited via closed diode contacts, right? So in the very first charging cycle, the output voltage remains 0 volts. Okay. So in your circuit, you are left with only two voltages, Vi and Vc. Of course, V0 you can include when you apply KVL, but eventually you are going to substitute V0 is equal to 0 volts. All right. Since we have started with the negative half cycle, so what we can do is we can apply KVL. Apply KVL in anti-clockwise direction. So, yeah, anti-clockwise direction, minus to plus Vi, and then minus to plus V0, and then plus to minus Vc is equal to 0. But we have already seen that output is 0 volts because resistor is short circuited. So, Vi minus Vc is equal to 0. That implies Vc is equal to Vi. As you can see, the capacitor voltage Vc is nothing but Vi. And what is Vi? Vi is nothing but the incoming input signal. Therefore, when Vi reaches maximum value in the very first negative half cycle, when Vi becomes Vm, let me write, this is nothing but the maximum value of the input. What about Vc? So when Vi is Vm, Vc is equal to Vm, which is equal to Vm. So the capacitor gets charged to maximum voltage of the. So from now on, capacitor can be treated as a battery. And what is the potential of the battery? The potential of the battery is Vm volts. Okay, so which is called as a DC restorer circuit. All right. So now let us discuss about the output. How this capacitor voltage is going to affect the output waveform. So let me redraw the circuit. So this is Vc, and remember that Vc is charged to what voltage? Vm volt. And also take care of the polarity. So this is how the capacitor was getting charged, right? Left hand side is minus and right hand side is plus. So the same polarity you have to insert while calculating the output voltage. Left hand side is minus, right hand side is plus. Okay? And where Vc is equal to Vm. So from the charging cycle analysis, we have obtained Vc is equal to Vm. Okay. Now, when you have to determine the output voltage, what you can do is you can start with positive half cycle. You can start with positive half cycle, and you need not carry out the analysis for negative half cycle, because the negative half cycle analysis can be simply complemented with the positive half cycle analysis. I'll tell you how exactly you are going to do it. Okay, so for the positive half cycle, let us assign the polarity. So for the positive half cycle of the input, upper side of Vi is positive and lower side of Vi is negative, right? And you can also mark the anode and cathode contacts. So during the positive half cycle of the input, as you can clearly observe that the minus terminal of the source is connected to anode terminal of the battery, right? So this leads to reverse biasing condition. So during positive half cycle, Vi keeps the diode in off state. Okay, what do you mean by off state? Off state is nothing but reverse biasing mode, right? So once the diode is reverse biased, you can remove the diode terminals with open circuit equivalent, right? So this is where the diode was present. Now you are going to remove it with an open circuit equivalent. And now you can apply KVL. So in this direction, that is clockwise direction, you can apply KVL. Apply KVL in clockwise direction. Okay. So minus to plus Vi, and then minus to plus Vc, and then plus to minus V0 is equal to 0. So output voltage V0 is equal to input voltage Vi plus Vc, which is also equals to Vi plus Vc. So in place of Vc, what did we get in the charging cycle? We have obtained Vc is equal to V, because capacitor is going to get charged to the maximum value of the input waveform. Okay, so for the clamper analysis, all what we need is this analysis. Output voltage V0 is equal to input voltage Vi plus Vc. As you can clearly observe that your output equation is consisting of a DC term. And what is that DC term? Vc term. So Vc is nothing but DC term, and the value of Vc is nothing but Vm. Vm is the maximum value of the input. We have obtained V0 is equal to Vm plus Vm. Right. So we can make a small table. Okay. So this is your Vi and this is your V0. So this is for the positive half cycle and this is for the negative half cycle. So in a single table, you can comment on the status of positive half cycle and status of negative half cycle. So in the positive half cycle, okay, when your input is 0, so let's say this is your input. So when your input is 0, output V0 going to be Vm plus Vi, right? So your output going to be Vm plus Vi. And what is Vi? Vi is 0. So your output is at Vm, right? So this is the maximum value of the input waveform. So what happens is that when your input attains 0 volt value, your output will attain Vm value, right? So in a similar manner, when your input attains plus Vm, what will be the value of the output? So your output attains Vm plus Vi. And what is Vi? Vm. And what's the total output voltage? 2 Vm. So when your input is at Vm, your output will be somewhere here. So this value corresponds to 2 Vm. And once again, when your input falls to 0, your output going to be there at Vm level. So this is how you will get the positive half cycle, right? Positive half cycle. So you can clearly observe that your output waveform is being shifted upwards by plus Vm volts. So your output is getting shifted in the upward direction. So upward movement is considered as positive sense, hence the resultant clamper is called as a positive clamper. Okay, and you can understand the status of the output with the help of this table itself, in the sense during the negative half cycle. Let me use a different color here. During the negative half cycle, when your input reaches 0 volts, okay, the output going to be Vm plus Vi. And what is Vi? Vi is 0. So output will be at Vm volts. So that means to say output is somewhere here. Okay. And when your input reaches minus Vm in the negative direction, what will be the status of the output? Output going to be Vm plus Vi. And where is your Vi? Vi is at minus Vm level. Okay, so plus Vm minus Vm leads to 0 volts. So when your input reaches negative maximum, your output reaches 0 volt level. Similarly, when the input reaches 0 volt level, the output reaches Vm level. So now you can complete the waveform. So when your input is 0, output is at plus Vm, and when your input is at minus Vm, output is at 0 volt level. 0 volt level. So as you can clearly observe that output is getting shifted by plus Vm level. Okay, since it is getting shifted by plus Vm level, it is called as a positive. In case of negative clamper, what could be your observation? In case of negative clamper, the output waveform is going to get shifted in the downward direction by minus Vm level. So that is the difference. Okay. And you can also derive a special note